So I wanted to make this video about even and odd functions, which is basically just a new way of talking about functions. It's a way to classify functions. Because if we can classify a function as even or odd, we get some really nice things that happen, some nice properties that we can kind of take advantage of. So this is a pre-calculus 1 topic, but I'm going to kind of go over it in general. And so the general idea is that we're interested in seeing what happens if we plug in negative x into some function, right? What happens if we plug that in? If we drop in negative x in here, there's 3 different things that could happen, okay? 3 things. One option is that we get out the same thing as if we had put in the positive version of that x. If that happens, then we say that the function is an even function. Okay, another thing that could happen is if we put in a negative x here and we get out negative of what we would have gotten if we put in the positive version of x, and that is what we call an odd function. And then something else could happen, which is we get out some random output that doesn't have any special property, in which case the function we just say is neither even or odd. So an example of such a function, or example of all 3, let's start with an even function, might be simply the function y is equal to x squared. And by example, we'll do it by example first. If I were to say plug in 3 into this function, we're going to get 3 squared, which is equal to 9. And if I were to plug in negative 3 into this function, we're going to get negative 3 squared, which is also equal to 9. So we can see that when I plug in the negative version of x, of some input, I actually get out the same exact thing as if it didn't have a negative in the first place. So that's really nice. And we can verify this, more concretely, because showing that something holds just for 2 numbers is not technically a proof. What will actually prove this thing in general is if we attack the problem in general. So like I mentioned before, if I put in negative x into my function, what do I get out? Well, I'm going to get negative x squared, which is equal to positive x squared, which is the same thing that I would have gotten if I had put in an x in the first place, a regular x. And so from this very small set of equations here, we get that f of negative x is equal to f of x, and this will always hold true for any x that I put into the function. This is really nice. And even functions have this really nice visual property that when you graph an even function, you always have perfect symmetry about the y-axis. So the idea is if I pick 3 over here and my y value is up here, then when I go pick negative 3, then my y value is going to be up in the same place. I have perfect symmetry about the y-axis. So an example of an odd function might be y is equal to x cubed. And so again, let's try and put in, let's say negative 3 inside, because that's really how we test. This all revolves around whether or not, when we put in negative x, what happens? And so if I plug in negative 3, I'm going to get negative 3 cubed, which is equal to negative 27. And if I had put in a positive 3, I would get a positive 3 cubed, which is equal to positive 27. And so you'll notice that this negative 27 here is the negative version of what I would have gotten if I put in a positive 3 in the first place. And so this is kind of how this is an odd function. But again, we want to show this a little more rigorously. So we want to test, if I put in negative x into my function, what do I get out? And I'll get negative x cubed, and that just becomes negative x cubed like so, which is, of course, negative of what I would get if I just put in x in the first place. So again, we have this nice equality that if I put in the negative x, I get out negative f of x. So it falls into the second category here, and this is an odd function. Now, one that might fall into the neither category, let's see, might be, well, let's try y is equal to x squared plus x. All right, and so by example, let's just kind of plug in -3. Okay, if I plug in -3, I get -3 squared minus 3, which is equal to 9 minus 3, which is 6. And on the other hand, if I look at, f of 3, I'm going to get 3 squared plus 3, which is 9 plus 3, which is 12. And so, if we take a close look at f of -3 here, the result is not equal to what I would get if I plugged in regular 3, and it's not equal to the negative version of that either. So it kind of falls outside being an even and odd function. It is neither. And more rigorously, how would you check this? We would simply just take negative x and plug it inside. And when we do that, we get negative x squared minus x, which is x squared minus x. And again, we have to remember that good old-fashioned f of x was equal to x squared plus x. So clearly these aren't the same. And if we look at negative f of x, that would be negative x squared minus x, and those are not the same. So it doesn't fall in either category, and these ones are neither. All right. Wonderful. Oh, I forgot to mention, what happens if you graph an odd function. So an odd function has its own symmetry, but it's a little more strange. This symmetry actually lies perfectly about the line y is equal to x. It's a little bit, it might seem a little bit strange. But you can kind of think about that as if I were to flop over the graph across the y-axis and then flop it over the x-axis, we would end up in the correct place. So for instance, if I flopped it over the y-axis once, I would get this. And then if I now flop it over the x-axis, I'm going to land right on the pink line. So what does this all have to do with trig functions, right? In the homework, we're learning about trig functions and properties of trig functions. And so, well, let's see what happens. So let's examine sine of x and cosine of x to see if they are even, odd, or neither. Let's see if they have any special properties. So starting off with sine of x. Okay, sine of x. So let's just kind of test some values, and maybe I will draw us a little unit circle over here just to kind of help us as we do this. All right. So if I consider, say, sine, just by example first, sine of pi over 4. All right, this is root 2 over 2, because if I go to pi over 4, that is going to be the y value that I end up at. Now, what happens if I were to have tried sine of negative pi over 4? Well, sine of negative pi over 4 is equal to negative square root 2 over 2. And that is the negative version of if I had plugged in, the positive pi over 4. Okay, so we have an idea that sine is going to be an odd function. All right, and so to prove this a little more rigorously, we can simply, again, just plug in negative x into sine. Okay. Now, this is a little bit strange for us to think about, but I will simply just draw our negative angle here. Let's say this is negative x degrees, right, like so. And so it's going to have some y value associated with it, right? We've gone some angle down. And so it's going to equal some y value. And it's probably going to be a negative y value. Now, in theory, I could keep wrapping and it'd be positive, but for simplicity of just making this argument, palatable for us, let's say that this y value here is a negative number. So it's like a negative y of some sort, okay? Equals negative y. But if I were to plug in, say, some positive value, okay, some positive value of x, if I go up the same exact amount, hopefully we can kind of see that the point we're going to land at is going to be the exact same y value, just positive. So this is not equal to the positive version. This is just the negative of what we would have gotten if we went up by x degrees in the first place. So it turns out, okay, what is like the grand result? It turns out that sine of x is an odd function. Okay, it's an odd function. All right, sine of x is an odd function. This means that if you see an equation that has sine of negative theta in it, this is the same thing as negative sine of theta. Or if you have sine of negative x, it's going to be the same thing as negative sine of x, so on and so forth. Now, what about good old-fashioned cosine of theta, right? What's going on with cosine of theta? All right, so let's run the same experiment. We'll draw ourselves a little unit circle. All right, draw ourselves a little unit circle and make some progress. So cosine of theta, let's try cosine of pi over 4. And again, that is also root 2 over 2. It's kind of up here. All right, and we'll notice that if I try cosine of negative pi over 4, we end up at, well, still root 2 over 2. It doesn't matter if I go negative or not. The x values are still the same, and so we can try to reason our way through this kind of logically. Let's say we have some negative theta that we go. We're obviously going to have some positive x value. Right? This is going to be some positive x value, but it turns out if I had done, positive theta in the first place, if I'd gone up theta degrees, I'd end up at the exact same x value, right? Nothing would be different there. So it turns out that cosine of theta or cosine of x or whatever variable you want to use is an even function. It's an even function. So this means if you see a homework problem or something of the nature where you're dealing with cosine of negative theta and you're like, oh man, I don't know how to simplify this, you can just rewrite this as cosine of theta. They are going to give you the exact same answer, so these are the exact same thing. That's really nice when we need to simplify algebra expressions that have cosine of negative theta in it. Now, maybe one more thing that we can talk about just as kind of like a little bonus that I didn't think I was going to cover, but I'll do it just now, is to talk about, the fact that since cosine is an even function, there should be that nice symmetry that we talked about, right, over the y-axis. And hopefully we know by now that, the cosine graph would continue on this side and so on and so forth. And it turns out that no matter where I cut it, if I go over some distance to the right and I go over the same distance to the left, that I have perfect symmetry about the y-axis here. So if I end up at this x value here and I go negative x in this direction, I'm going to end up at the same exact y value. So visually, cosine of x being an even function checks out. What else do we have to talk about? We have, of course, sine of x, and sine of x is an odd function, a little bit trickier to draw and to understand visually why it's an odd function, but I'll do my best anyways. So here is, sine of x, and if we had continued it onto the other side, let's see if I can do this. If I continued onto the other side, it kind of looks something like this. Right, and it's kind of a poor drawing, but the idea is again, as promised, if I were to flip this graph over the x-axis and over the y-axis, right? So if I flip it over the x-axis, we get we get here. And then if I were to now flip it over the y-axis, hopefully we see that if I pick up this orange piece and flip it over there, it would land on top of the graph, and we would have our symmetry that I mentioned earlier when talking about odd functions. Where was it? Up here. All right, so what are the key takeaways here? The key takeaways are just this definition. It's a very strange definition at first when we're not familiar working with it, but it has nothing to do with the exponent power because, you know, as we clearly saw, if you want to say, oh, this is degree 2, it's going to be even, well, you'd be wrong. And then I'd say, well, the degree of sine and the degree of cosine here are both, you know, exponent 1, and they're clearly different. They're different in terms of being even or odd. So it has nothing to do with the exponent itself and has everything to do with, does it follow this pattern? If you put in a negative x into your function, do we get out the positive thing? Do we get out the negative version of what we would have got if we put in the positive thing? Or do we get out something nonsensical that doesn't follow any particular pattern at all? And again, the purpose of doing this is that if you can identify that something is an even function or an odd function, that basically it follows this pattern for all sorts of numbers, it's really nice because if I tell you, for instance, maybe over here on the right side, I'll just do a quick example. If I were to tell you that f is an even function, okay, even function, and you know that f of 3 is equal to 21, and then I asked you to figure out what f of negative 3 is, you could immediately tell me that the answer is going to be 21. You don't need to know anything about the function. You don't need to know what the function is. You don't need to know how to evaluate it at negative 3. Because you already know this is an even function, you can immediately spit out this information, which is really nice. You get to do like half the work. You get 2 answers for the price of 1. And that's something that's really useful. So that's going to do it for even and odd functions. Hopefully that made sense. Again, you know, sine is an odd function, cosine is an even function, and hopefully you put those to good use.